All right, so before we go to the summation for the geometric sequence, I want to just do an example of the sum of an arithmetic sequence. So here's an arithmetic sequence that I put there, 27, 30, 33. By the way, just because it looks like an arithmetic sequence doesn't mean it has to be an arithmetic sequence. So like you can't really answer this question, where's the first 200 terms of, unless you know, unless it's stated that this is an arithmetic sequence. So, where, so I have to say this is, I wish I'd put it up here, this is an arithmetic sequence. I'll actually talk about that a little bit after we do this. This is an arithmetic sequence. All right, but I don't know that just from looking at the terms. I have to be told that. All right, so once we know it's an arithmetic sequence, we know we have A1 equals 27 and D equals 3. Then we can just plug into our formula S sub n equals n times A sub 1 plus n minus 1d over 2. So that is, we want to add up 200 terms, so it's going to be 200 times our first term, which is 27, plus our n minus 1 is going to be 199, times our difference, which is 3, all over 2. Yeah, that's not too hard to do actually in your head, really, because 2 times 27 is 54, so you get 5,400. And then when you do this, I would just cancel the 2 and the 100, the 2 and the 200, so you have 100 times. And then how could I do 199 times 3 easily? Well, it's 200 times 3 is 600, but I'm going to be short 3, so it's 597. Right, so then it's pretty easy without a calculator to get that's 5,400 plus 59700. Then for some reason when I was doing this, I could do all that in my head, but I couldn't do this in my head and I had to write it out. I didn't get my calculator though, I just wrote it out. Anyway, it's 65,100, that's the sum of the first 200 terms of this sequence, as long as we know that that sequence is arithmetic. All right, sequences do not have to be arithmetic or geometric, and they cannot be judged by finitely many terms. So you have to have some way to know something about the infinitely many terms. So for example, as long as we know this is an arithmetic sequence, then we know not only the terms that were shown, we know all of the terms because it's an arithmetic sequence. But let's say I had this sequence, 3, 5, 7. What do you think the next term is? What do you think the next term is? 3, 5, 7? Nope, it was 11. All right, what do you think the next term of the sequence is? It's 13. And then 17. What do you think my sequence is? All right, what do you think my sequence is? Is the sequence of the nth prime numbers. So this is the sequence, the nth prime from n equals 1 to infinity. All right, it's not arithmetic, it's not geometric, does not have any explicit formula at all. What else? I had another example in my head, and I forgot what it was. Oh, here's a good one. Here's a sequence. What do you think the next number is? It's 2. What's the next number? It's 6. What's the sequence? The nth digit of pi. All right, that's an infinite sequence, right? Okay, yeah. You know, there are other kinds of sequences. By the way, for example, we can have the sequence 2, 2, 2, 2, all right? This is a geometric sequence with r equals 1 and a sub 1 equals 2. It's also arithmetic with a d equals 0 and a sub 1 equals 2. Here's a good sequence for you to really illustrate what it means that a sequence is a function and a function is a set of ordered pairs, right? So here's my sequence. What's the next number? Next number was 7. How did you know that? What are these numbers? These are just the numbers that popped into my head. All right, so this sequence is the nth number that I thought of. So what that is to illustrate is that a sequence does not have to have a rule. All right, so all the sequences that we've looked at so far, this is the sequence a sub n equals 2, right, from n equals 1 to infinity. We can write a rule for them. This one we can write a sub n is, now I got to figure this out off the top of my head. It's 27 plus n minus 27 plus 3 times n minus 1 from n equals 1 to infinity. So a lot of the sequences we're really interested in have rules to them. All right, maybe it's something you can write like this. Okay, but a sequence does not have to have a rule because the sequence is a function. The function can be any set of ordered pairs. So I always come back to this definition: a function is a set of ordered pairs. There's no reference to a rule or a pattern in the definition of a function that I use. Now, by the way, you're going to find a lot of textbooks that do specify something about a rule or a pattern. But rule or pattern is essentially an undefined term. The rule could be, what is the next number that a porpoise thinks of. I do have one book. Can I get it while that video is running? Will that be worth doing? Okay, it was totally worth it. This one, Topics in Algebra by Herstein. This was my textbook for modern algebra. What you will learn when you take a course in college called modern algebra, you will learn that you actually don't know any algebra. Let's see, we'll find our definition of function here. Intersection, union. Oh, I'm going to regret having looking for this because I didn't mark it ahead of time. Mappings. We got a definition of function here now. Now you get to see me scrolling through pages. Well, I probably should just save it for the next video. But look how stubbornly I keep looking for the definition of function. All right, I'll put it in the next video.